Okay, welcome everyone. So we will wait for 5 more minutes to see if other participants join, then we will start. Okay, anyway, let's start. So just to make sure you are joining the right course, this is NOC EE-91 NPTEL tutorial on semiconductor devices and circuits. The course instructor is Professor Sanjeev from ISC Bangalore. I am Debashish Nandi from IIT Kanpur. I am a TA assigned to this course along with Atib Nasir. The duration is all you know that it's a 12-week course and we go live every Sunday 5 to 7. Okay. So some prerequisites. You are expected to at least have gone through the last week's lectures posted on the course web page. This I found difficult to explain some concept in last week because you were not ready with the lectures, right? You haven't seen the lectures properly. So it is not possible for me to explain each and every concept. So sometimes it is required that I go on to the explanation of the problem directly. So I may not be able to derive that formula particularly used because it may get very lengthy. So it is again requested to you that please at least have gone through, at least have go through the lectures. and also you should have at least attempted the assignments. Okay, then only you can ask the doubt in this kind of discussion session. Please keep your microphones muted all the time. If you have any question, if I have any question, I'll ask you to unmute the microphone, and we can then discuss. Okay. And also, if you have any query, general query at the end of the second hour, I will try to assign. I have been trying, actually. It was not possible, but let's see. If we get some time, we can discuss some general queries. Okay. And the recorded lectures, I think you have got the link by now. Okay. So let's proceed. So this is week 3. So let's start with the first question. These are the first two questions or the leftovers of the last week. Okay, I could not complete the last two questions I planned to, so I am starting with those. Okay, it is mentioned that Bloch's theorem for a periodic potential is given by this quantity. Okay, this, where A is the lattice constant. Assume that Ux is the periodic lattice potential given by this. Note that periodic terms and equivalent formulation of the Bloch theorem. Okay, so it is pretty simple and straightforward, but I want to mention some critical aspect to it. Okay, so what is this U? Can anyone tell me what is this U we are talking about? Suppose this is your crystal locations. Okay, please confirm that you are at least able to hear me. Can
U is the periodic potential.
Okay, you can listen to me, right?
Yes, yes,
Okay.
yes.
So U is the periodic potential. So what potential we are talking about? You remember in the chronic Penny model, we had these are the nucleus of the atom, and we had the potential profile like this, right? And we assume that it is an infinite periodic lattice, infinite periodic atom, right? Infinite periodic crystal, right? So how will the periodic potential will look like? It will look like this, kind of this, right? So you see, these are the periodic nature of the potential. This is what we are talking about as U of x. Okay. So this is periodic. And what is the period? This distance, right? A. After every A distance, it will get repeated. So that is what potential we are talking about. Now I wanted to make one point clear. Okay. So let's start with this Schrodinger equation. So del square psi by del x square plus V of psi equal to E of psi. Okay. So this is very well known to us. Now let us simplify it. So we'll have minus 2m by h square e minus v of x and psi of x. Okay. So v psi all are function of x. Okay. So can we write it in this form where your f of x is okay? So we know that this potential is periodic, right? From here, periodic with period a. That means v of x plus a is v of x. Okay. So we can write that f of x plus a is equal to f of x. Is that okay with you? That if this is periodic and these everything's are constant, so f of x is also periodic with a. Okay. So now I do one trick. This, let's say this is equation 1. Replace x with x plus a in this equation. Okay. So what do we get? Plus f of x plus a psi of x plus a equal to 0. By the way, can anyone tell me what is the solution of this equation in terms of psi?
A cos kx plus
No,
x.
that is for a particular case, right? Psi x is the solution to this equation. Okay, psi x can take any form depending upon the boundary condition and the energy profile. Okay, so psi x is the solution. Suppose you are writing a equation x square plus 2x plus 1 equal to 0, right? The solution is x. It can take any value, right? It can take -1, two values of -1. Okay, so similarly, what I want to show is that now what you do to this equation, can I write it in this form? X plus a dx square plus, we know that this is f of x into this equal to 0. Can I write this from this? Is that okay with you? Even if not, let's say d of psi x plus a over d of x plus a. Okay, I can write this as d of x into d of x plus a over d of x. Sorry, d of x over d of x plus a, right? This term is 0. This term is 1 because d of x plus a over d of x is 1, right? A is constant. So I can from that second derivative also I can write this term. So from this equation, what you can notice that psi of x plus a is also a solution to Schrodinger equation. Okay, more precisely TC, time independent Schrodinger equation. Okay, so now tell me one thing, can I conclude that psi of x satisfies Schrodinger equation? Psi of x plus a satisfies same equation. Can I write this? Can anyone comment on this? If one value satisfies two values satisfies the same equation, does that mean that the two values should be same?
No, sir.
So not, right? May not be same. So note this point very carefully. Okay, that your, what is the takeaway from this, that u of x or v of x is periodic. Okay, with period this is valid, but my psi of x is not periodic. Okay, may not be periodic. So never confuse this thing. Okay, the potential profile in a crystal is periodic, but psi of x is not periodic. Okay, it may be periodic, but it is not periodic generally. Okay, so this is the point I wanted to bring out. Now as far as the question goes, okay, so this is given, it is given that let me do it here. Given what? Psi of x plus a is equal to e to the power I k a into psi of x, right? Yeah, that is what is given. So what I do is that I write it in this form, okay? K a plus x and then negate it. Okay, is that fine? So now what I do? Psi of x plus a into e to the power, this comes out to be minus I of k x plus a. Okay, so this term is periodic with a, this entire term is periodic with a, fine. So let me call it u of x. Okay, because I know I have a potential function which is periodic as x plus a. Okay, so let me call this entire thing which is periodic, not psi but psi of x into e to the power minus ikx. Okay, that term is periodic. That shows me a potential profile. So what do I have? I have this. So can I conclude with this? That with the given information, it is where your u of x is u of x plus a. So what were the given information to us in the question? This term was given and this thing was given. So from that we can conclude that this can also be written. Okay. So this is called Bloch's theorem. So your D would be the right option. Fine. So the takeaway from this question is that psi of x or the solution of the Schrodinger equation may not be periodic, but the potential profile is periodic, which is related to the solution of the solution of the Schrodinger equation by this equation. Okay. Okay. So I think it is pretty clear. If you have any question, you can ask at this point. Okay. So let's move on to the next problem. This is also from the last class. Okay. So it is mentioned that one molybdenum crystal is a body centered cubic one. Okay, with a lattice constant of this. Okay, first let us draw the body centered cubic one. So where at the position of the atoms? As it is cubic, 8 atoms should be at 8 corners and one atom would be at the center of the any body diagonal. Okay, so let me just name it F H. Okay, so let me connect one body diagonal. and at the center there will be the other atom. Okay, so let me call this atom as BC, body centered. Okay, so now in the question it is now tell me 2-3 things. Okay, what is the distance BE in terms of A? If this is A, small a, then what is the distance BE, the body diagonal? Anyone? Root 3a. Yeah, right, root 3a. Okay, so how does that come about? Just consider this right angle triangle. Okay, this right angle triangle. So consider this BDE. Okay, angle BDE is equal to 90 degree. Fine. BD, you know it is root over 2a because it is the diagonal of that square. So your BE would be from your Pythagoras theorem BD square plus ED square. Okay, that is your 2a square plus a square, that is your root 3 of a. Fine. So now tell me, there are two atoms. Okay, consider, focus on this line, that if the radius of the molybdenum atom is 1/2 of the center to center spacing of the nearest neighbors, can you tell me what are these two nearest neighbors? Which two atoms could be the nearest neighbors? This A and B has a distance spacing of A, right? What about this BC, atom BC, and any of the edges? This distance would be your root 3 A over 2, right? So this is how much? 0.866 A. That is your less than A. That means whenever we are talking about nearest atoms, it is this atom and any one of this atom. Okay, so now in the question it is given that suppose these are the two atoms. Okay, if the radius of the molybdenum atom is 1/2 of the center to center spacing of the nearest neighbors. Okay, that means they are talking about this scenario. So this is your, let's say this is your atom B and this is your atom BC. Okay, so they are telling that this distance is half of the center to center distance. Okay, so if that is the case, then these two atoms should touch each other. So what is this distance? The radius of the atom, it is nothing but your root over 3a by 4. Okay, and if I just extend it to the other side, so this would be your point E. Okay, so now tell me number of atoms in one unit cell of molybdenum is, it is a body centered cubic, right? So it should be 2. This we have discussed in the last class, that one center atom and 1/8 of the 8 corner atom, that gives me 1 plus 1 is 2. Fine. So can we calculate the total volume occupied by the atoms? It should be 2 into the volume of one atom, right? The volume of one atom, and that is 4 by 3 pi r cube. R is the radius. What is r here? R is my root 3a over 4 cube. Okay. And what is the volume of the cube? Volume of unit cell? It is nothing but your a cube. Okay. So what is the percentage occupied? Is nothing but your this 4 by 3 pi root 3a by 4 cube over a cube into 100%. Fine. So this will give you 0.68 into 100%, because this a cube will get cancelled, and other just constants. Okay. So it will give you around 68%. Okay. So your C would be the right answer. Is it okay? Last class, someone has doubt visualizing this lattice structures. So that's why I am asking that.
Yes, sir, it is clear.
Yeah, it is clear, right? Okay, fine. So let's move on to the next problem. Okay. So it is given that given energy band diagram, how can one find the electric field? Okay. Let me give you some insight to this. First, tell me the difference between band structure and band diagram. These are very confusing, so it should be cleared at this point only. Okay. So what do we mean by band structure? Can anyone unmute and tell me? Last class I have discussed. Band structure is nothing but your EK diagram. Okay. So let's say this kind of diagram you will find. Okay. This is your conduction band minima. This is your valence band minima, valence band maxima. Okay. And this is your energy gap. Fine. And from the curvature of this, what do we get? Anyone unmute and tell?
Another forbidden energy gap.
Sorry? Can you please repeat?
Gap, the forbidden energy gap.
No. From the curvature of the band diagram at the conduction band minima and at the valence band minima, we get effective mass, right? M star.
Correct.
M of E star is equal to h bar square by del E square by del K square, right? At the conduction band minima. Similarly, for hole it is valence band maxima. Okay. So this we have discussed in last class. So this is band structure. Okay. By the way, K is a vector I have mentioned. So you will find out that if you do in further studies or higher studies, some very complicated band structure. This is the simplest one. It is similar to the free energy or parabolic approximation. Okay. So there will be very complicated structure, and you will find that some gamma point, some x point, etc. planes are there, and there will be some Miller indices written in this. Okay. So K is a vector. Remember, it is a three-dimensional quantity. For the simplicity, we are just taking it as a one-dimensional thing. Okay. As of now. So this is called your band structure. Okay. So what is band diagram? So just let me draw it here. So what is the atomic number of silicon, by the way?
14.
Can you tell me the combination in this form? 1s2, 2s2,
1 is to 2 is to 2p 6.
then
3:3p2.
3s2, 3p2. Okay.
3p2.
So now just let me draw it in this fashion. This is your 1s, 2s, 2p, 3s, 3p. Okay. And I am showing the empty states available in this fashion. 1s has two states, 2s has two states, 2p has 6 states, 3s has 2 states, and 3p has 6 states, right? Because p orbital we know
Yes.
has 6 states.
6 states, 4 empty.
Now in silicon, what happens is that these are filled. And any two of the 3p will be filled. Okay. So now if I draw A in this axis, A is the lattice constant or the lattice spacing. This periodic spacing, this spacing is A. Okay. So if I go this way, A will decrease. Okay. That means this will become the structure of the atoms. Okay. So if it is A2 and it is A1, A1 is less than A2. Okay. So this is that A. And at infinite, the electrons, two electrons does not have any coupling between them. Okay. So they are far apart. So their energy states will seem like a discrete one. Okay. Just like I have drawn here. So now if I draw energy at this axis, and if I start to reduce my A, and what do we mean by reducing A? When we reduce A, that means we are bringing the crystal atoms close to each other. That means the outer shell of the atoms will outer shell of the electrons, outer shell electrons will start of the two different atoms will start to interact with each other. Okay. So what happens? This 1s will not get splitted. Okay, because it is a very core to the very close to the nucleus. Similarly, your 2s will not be. So this splitting or band splitting happens when two of the electrons try to occupy a same energy state. Okay, we know from Pauli's exclusion principle that it is not possible for a fermion like electron. Okay, so what happens to the valence band? Your 3s and 3p starts to split. Okay, let me draw it properly. It shows your this kind of just have I drawn it properly? 12 split, and it will split like this. This band will start to split and this band will also start to split. Okay. So it will create somewhat this kind of shape. Okay. So what happens to the semiconductor is that semiconductor case, it is such that your atomic distance falls at around this region. Okay. Your A for semiconductor falls around this region. So what happens is that of the you have total 8 states. Okay. 6 available, 6 available, 2 filled. Okay. Here 2 available, 2 filled. So at this place what happens is that in this place it happens such that 4 are available and 4 are filled, and in this case 4 available, 0 are filled. Okay. So this creates your conduction band and this creates your valence band, and this distance creates your band gap in semiconductors. Okay. So what happens actually, the interatomic distance of semiconductors are such that it falls in that region where the band starts to split, because the neighborhood of two atoms are very close. Okay. So the band starts to split and it creates two bands, conduction band and valence band. Okay. So do we call this as band diagram? This is not band diagram. Okay. This is your E versus lattice constant diagram. So remember these things, that whenever we are discussing, just let me add one page. Okay. So whenever we are discussing in semiconductor physics, we see 2-3 types of energy diagrams. Okay. So now if I just take this point and draw here, only I am looking at this point. Okay. So I see what? This is my this point and this point. This is my EC and this is my EV. Okay. And this is the band gap for a particular A. Now suppose I move along the crystal. So this is my EC, this is my EV, this is my X direction along the crystal or distance along the crystal. Okay. This is my valence band maxima, this is my conduction band minima. Okay. So this kind of diagram we call band diagrams. So if I call you, if I ask you that, tell me what in band energy band diagrams, what is the y-axis and what is the x-axis? What will be your answer? Anyone?
X-axis is energy.
X-axis is energy. It is written here, right?
Y-axis is energy, x-axis is distance between them.
Distance between what?
Electron.
Y-axis is energy, x-axis is carrier concentration.
No. y-axis is energy, x-axis is distance along the crystal. Suppose this is your crystal, okay? Say this is a bulk crystal. Don't confuse it with your unit cell, okay? It is not unit cell. This is suppose a piece of silicon, okay? Some bar of silicon. Fine. Now let me call it x equal to 0 and x equal to some distance, let's say L. Okay. So the energy, conduction band energy, just let me use another color. So the conduction band energy, let's say, varies like this, and this is the valence band energy. Okay, this is EC, this is EV. So EC and EV are the energy levels. Okay, y-axis gives me the energy level of the conduction band minima and valence band maxima. Okay, and x-axis give me the displacement along the crystal. This is along the crystal I am moving. So band diagram, always remember that whenever we are talking about band diagrams means your energy levels, how your conduction band energy level varies along the crystal, okay, or along the semiconductor block or material. Is that clear? Because you are giving me very funny answers. Someone said concentration. How can we haven't even talked about concentration yet, right? So it is how your energy varies along the material. Okay, suppose this pencil is a semiconductor block. So this is how your energy, if your energy is straight, you will see a straight line. So this is how my energy varies along this pencil or this material. Okay, so that is my energy band diagram. So now suppose you have a energy band diagram like this. I am just considering here EC. Okay, EC generally takes the form of minus Q of potential plus some constant. Okay, so what happens is that suppose in your material, your just let me take another material. Suppose this is a block of silicon. Okay, so suppose your energy is varying like this, that means your potential will be varying like this. Okay, it is just some negative constant times this is your phi profile will be like this. So can we have this kind of potential profile in any material? Please, I want you to discuss, because this is very important concept and there are many misconceptions regarding this. If you don't get it cleared now, it will be there for in your mind. The wrong concept will be there in your mind forever. Okay, so please ask questions if you do not understand it. How can I get a positive potential and a negative potential? Please unmute and tell me. I want to discuss actually, because then it will be very helpful. It is okay that if you give me wrong answer, I will explain it again. Okay.
If it is at higher energy level, then it is positive potential. It's a guess. I don't know.
Okay. So first tell me, what do you mean by potential? Suppose you have a battery, right? Suppose you have a battery like this, can you have a positive and negative potential at both ends?
Yes, sir.
Right, your battery's positive terminal is at higher potential, obviously, right?
Yes, sir.
So you can have this kind of profile in any material where at one end you have higher potential and another end you have lower potential. Okay, this is the conventional circuit potential what we are talking about. Now what is this EC? Remember that EC is electronic energy. Okay, EC is electronic energy. So at high potential, and this is low potential, let's say this is high potential, this is low potential. So what is the lowest energy for electron? Suppose this is an electron. Okay, we know that any entity in this universe tries to go to its ground state or lowest energy state. Okay, that is from thermodynamics we know. So what is preferable for electron to go, lower potential or higher potential?
Lower potential.
Why? Electron would like to get
For
attract.
stability.
No, that is why where the misconception will come, right? We are talking about electrons, not holes. Remember that. So electron, suppose there is some positive charges, okay? That means there is some higher potential. So if I have an electron nearby, will it try to go away from the positive charge or will it will try to get attracted to the positive charge?
Attracted to the positive.
Attracted to the positive charge, right? That means that is the natural path for the electron. That means that is the ground. Why it is getting attracted to the positive charge? Because it wants to get to the lower energy state for the electron. So higher potential means lower energy state for the electron. Okay, that's why this negative sign is there. If you still do not get it, let me explain it another way. Your energy is proportional to charge into potential. Okay, now you are talking about electronic energy. Electronic charge is negative and potential. So you see that if your potential increases, your electronic energy decreases. Yeah, I think it has lost. Now it is coming back. So do you agree that if at higher potential my electrons will have lower energy? Just tell me this much. Have you understood this much? That at higher potential my electrons will have a lower energy.
Yes.
Anyone who does not get this concept, because this will be applicable in each and every discussion we are having following in the course also and each sessions also. Okay, so it is very important to understand that higher potential, conventional potential gives me lower electronic energy because electrons prefers positive charges to go towards positive charges, and positive charges means higher potential, and electron will go to where it will have a least energy. Fine. So if potential is high at this point, here my electronic energy will be lowest. EC gives my electronic energy in the conduction band. Okay, so you see How this is just a constant, okay? So this relation is fine with you, right? The logic behind this relation, as my potential increases, electronic energy will decrease, okay? So I have EC equal to minus Q of potential plus EC0, okay? Now what I do differentiate this, minus Q d phi of dx plus 0, because this is constant, EC0 is constant. So my dEc of dx is nothing but Q of minus d phi dx. What is minus d phi dx? What is the negative gradient of potential? It is nothing but my electric field, right? So your electric field is proportional to dEc over dx. That means the slope of conduction bands, slope of conduction band give me directly the value of slope of conduction band divided by Q. Some electronic charge give me directly the value of electric field, okay? So given an energy band diagram, how can we find out electric field? It is proportional to the slope of EC, okay? So suppose you are given a energy band diagram like this, okay? This is, let's say, your EC. This kind of energy band diagram, by the way, is for PN junction, and you will see this in future classes, okay? And this is EV, suppose, let's say. So what will be the direction of my electric field? Can anyone at least attempt this question?
Valence to conduction.
Suppose this is my region A and region B, okay? Okay, no, Tanish, this is just another energy level. Let me just remove it, okay? Suppose this is my EC. So how will my electric field will be from A to B or B
Right.
to A?
B to A.
Why?
Because electron move downwards, so energy will be opposite of that.
Why it will move downward?
Recently you said that electron have higher electron at higher potential are more stable.
Right. So you mean to say here I have higher potential?
Yeah.
And how can you say that? You mean to say that my potential profile will look like this?
Yes, sir.
Fine. So that
Yes,
means
sir.
I have a positive, some positive charges I can assume here, and some negative charges I can assume here.
Yes, sir.
So field direction will be at this way.
Yes, sir.
Right. So you are right. Similarly, understand from this diagram only. Suppose you are standing, you are an electron, you are standing here, okay? You will try to go to the lower energy state. This is energy, right? Electronic energy. It is just like the slides in the parks you have, right? You climb up, you have at a higher potential energy because your mgh is higher. Then you slide it down. Because why do you get slided down? Because that is a lower energy level. Similarly, electron will try to go to the lower energy level, and this lower energy level means higher potential. Obviously, if I have an electron here, it will try to go to the opposite to the electric field. Fine. So if I give you any kind of profile, you can tell me how the direction of electric field will look like. Suppose this is my point A, point C, and this is my point D, and this is EC. So what is how the direction of electric field will be? C to D or D to E? This will be, I want Tanish to answer this. Tanish, can you please unmute and attempt this question?
Yes, sir.
So I was asking that if I have 2 points, okay, suppose in the silicon block you have 2 points C to D, and you know that your this is your EC profile or conduction band profile, okay, this you can get from band diagram. So can you
Yes, sir.
attempt to tell me that what is the direction of electric field, right to left or left to right?
It's C to D.
It will be C to D, and how do you tell that? What is the logic behind it?
Stability of electrons.
No, that is fine. But first step is you draw the potential profile. Okay.
Yes,
This
potential.
is your phi. Phi is higher at C, lower at D. That means there is some positive, some negative charges. Then only we have some higher potential, right?
Yes, sir.
So obviously electric field will be in this direction. So now if I give you any profile, can you tell me that where is the electric field? This you should be able to do, right?
Yes, sir.
Okay. So if you have any doubt,
Sir,
again I am, yeah.
Sir, once again you explain how C is at higher potential.
How C is at higher potential?
Yes.
Okay. Just let focus on the left hand side diagram. Okay. It is electronic energy. Okay.
Yes, sir.
So electron, not electron, any matter, any particle will try to go to its lower energy level,
Yes, sir.
right? So electron will try to fall down to lower energy level.
Yes, sir.
So this is electron's preferred spot. This is preferred spot.
Yes, sir.
Now tell me, if you have some charge distribution in a material, in which kind of cations or anions, or say positive charges and negative charges you have, electron will try to move to which kind of charge?
No, sir, this is not problem, sir. Previously, I think like that only.
Okay,
But if we assume that there is a electron and it go downward, then it's
right,
okay. But the electric field is in opposite direction.
right. So where is the problem?
Any other way?
No,
Whole,
no.
matlab,
If you take positive
whole.
charges,
If
right?
No. If we think about like there is a hole at point A and it
There is a
rolled down
hole at point A. Okay.
and it go downward,
Why
like
will hole?
electron go downward.
Why will hole go downward? It will not
No,
go downward, right?
yes, sir. I know. I had memorized this hole go upward and electron go downward, downhill and uphill for
No,
the
no,
MOSFET.
nothing to be memorizing. Okay, don't memorize anything. Simple thing. Again, if let's forget about holes. Okay, I will introduce holes in a while. Suppose you have this kind of profile. Okay, I am giving you that it is my electronic energy and it is my potential profile. Okay, now you place the hole. Let's say now you okay. Let's say now you place the hole at this place. Okay.
Yes, sir.
Similarly, the hole will be here also. Same
Yes, sir.
location, right? This is A only.
Yes, sir.
Now tell me that if I have a positive charge, hole is a positive charge.
Yes, sir.
will it go towards the positive charge?
No.
It will not go, right? So that's why I
Yes.
told it will go opposite to the positive charge. That means it will try to move
No,
at
sir.
this. Yeah.
Sir, sir, my question is that only ki why that is positive charge. Matlab, why it is at higher potential. If we assume that is it higher potential, then no problem. But
No. You
I
told
don't
you
know.
asked me that hole is at position A, right?
Yes, sir.
So that is by default it is at higher electronic potential as per my
Yes, sir.
diagram, right?
Yes, sir.
You want me to tell you if hole is here, what will happen?
Yes, sir.
Okay. So let's say your hole is here. That means hole is here. So hole
Yes,
will
sir.
try to move towards the negative charge.
Yes, sir.
That means hole will try to go climb up upwards.
No, sir. Sir, my question is not ki whole will. Sir, first my doubt is why you have written positive and negative.
Okay. Oh, the positive and negative. This is not for holes and electrons. Okay, this is make to make you understand that how the if we have a potential profile, right? Something is at high potential and something is at low potential.
Yes,
So
sir.
the net positive charge will be towards this. Okay.
No, sir. Sir, higher potential, sir, that is at higher potential and that is at lower potential. How you know about this?
Now I have taken the okay. I have given you this band diagram. Okay, this is given.
Yes, sir. Yes, sir.
If I know the band diagram or electronic energy, I can automatically draw this. Do you get it?
Yes, sir.
This is given, right? This green curve is given,
Yes, sir.
and from that I draw
After,
the red curve directly.
yes, sir. Means in green curve, where is at higher become lower and lower become higher.
Yes, obviously, because that is what I have been explaining, right? You see, every curve has been just becoming opposite. When you go to the electronic energy to potential, there is a minus sign, right? This minus
Yes, sir.
sign makes the plot just opposite.
And minus sign come due to?
Due to it, see, the potential we are talking about for positive charges, right? High positive charge means high potential,
Yes, sir.
and high electronic energy means high negative charge.
Yes, sir.
So you see the oppositeness of the charges.
Yes, sir.
That from that point the negative sign comes.
Yes, sir.
This place I have explained, right? Energy is
Yes,
proportional to
sir.
your potential into charge. Now for
Yes, sir.
energy we generally consider electronic energy, and for potential we
Yes,
generally
sir.
consider conventional potential. That means positive charge means high potential. So this difference of polarity of the charges introduces this negative sign.
Yes, sir.
Do you get it now?
Yes, sir.
So if I give you any energy band diagram, you can tell me in which direction the electric field is, how the potential profile will look like, right?
Yes, sir. Yes, sir.
Okay. So this was a very important concept. If you did not understood it, if you did not understand it, please revisit the recorded lecture again. I think you will get it. Even if you do not get it, then ask me in the next class. I'll explain it again. Okay?
Sir, before that, I only
Yeah.
marked that higher, high to low. Thank you, sir.
Okay. Okay. So let's move on to the next problem. Okay. So it is asked that consider an N-type semiconductor. First information given is that it is an N-type semiconductor. That means I have dopant atoms present, 0 Kelvin temperature. Where do you expect the Fermi level to be? Okay. Now I will start drawing the band diagrams. Okay. So if I draw this, let's say this is my EC, this is my EV. What are other energy levels I should draw for a n-type semiconductor?
So
What is the
donor level,
first thing? Sorry.
intrinsic Fermi level.
Okay, let us draw intrinsic Fermi level. But does it matter for a n-type semiconductor? It is by default n-type, right? It has lost its intrinsicity.
Yes.
So first thing is that n-type semiconductor. Okay, let us go step by step. N-type semiconductor means there should be some donor atoms, right? Donor atoms has to be there to form a n-type semiconductor. So donor atoms has to have some energy level. Let's say this is the energy level of donor atoms. Let's call it ED. Fine. Why, by the way, why do I draw this line as continuous, this line as continuous, and this line as discrete dashed line? Can anyone tell me? Do you know it? Okay. So you see, when you have energy in crystal, when you have energy profiles like this, you have discrete energy levels here, right? But suppose your electron are able to get out of this and able to get to this region, then it is having a continuous band of energy. Okay,
The gap is directly proportional to L. So L
right.
increases
L,
and
L
gap
increases,
decreases.
gap decreases. We can assume it like a continuous band. Fine.
Yes, sir.
That means your electron can move around from this place to this place. Fine. So that's
Yes.
why we draw the energy band this as a continuous line. Okay, to make you understand that electrons can move from any of these places equally. You remember that this is the x direction, this is the distance. Okay, now why do I draw these dopant atoms like this? Suppose you have a one dopant atom per 10 to the power 6 silicon atoms. Okay, so suppose you have a crystal structure like this, and in 1 million or 10 lakh silicon atoms you have one dopant atom. Okay, again after 10 lakh silicon atoms you have one dopant atom. So you see the distance between two dopant atoms, it is not continuous energy of dopants, right? We can assume the dopant atoms to be very far apart. Fine. So their bands don't split and their energy levels don't split and don't create some band. Okay, so that's why we mark the dopant energy level as a dashed one. That means that movement of electron from this to this is not easy. So electron move here to here, then here, and then can come here. But movement from this to this is not very simple. Okay, not easier for the electron. That's why we use it as a dashed line. So never draw dopant energy level with a continuous line. This is the logic behind that. So now, can anyone tell me what is the Fermi function you have been reading? This is of this nature. Have you seen this earlier?
Yes, sir.
Okay. So now tell me, at T equal to 0 Kelvin, f of E comma T will be 1 over 1 plus exponential plus or minus infinity. When it will be plus, this plus will be when E less than EF, sorry, E greater than EF, and this minus will be when E less than EF. I will stop here and just ask you, have you understand this part? Have you understood this part?
Yes, sir.
Please explain for E less than EF how it should, why it should be minus.
Greater, if that is greater than 4, -4 -2 is -2.
So let's say E
Simple mathematics.
is 2, EF is 4. Okay. So I have -2 by 0. So that will be minus infinity, right?
Yes, sir.
Okay. Okay. So this part is, if this part is clear to you, can you tell me that for E less than EF, what will be my f of E comma T? And for E greater than EF, what will be my f of E comma T? It will be 0, it will be 1, right?
Yes, sir.
Because e to the power minus infinity is 0, e to the power infinity is infinity, okay? So in one case you
Yes.
are getting 1 over infinity, in one case you are getting 1 over 0, 1 over 1 plus 0, okay? So what is this? What does this quantity mean? This is probability of occupying energy level E at temperature T, okay? So one thing is that my EF, we have been asked what the location of Fermi level, right? So one thing is that my EF has to be either greater than E or less than E, okay? Fine. Now another thing is that what is ND plus? ND plus means the number of dopant atoms which got ionized, okay? What is this quantity at 0 Kelvin? Means if your temperature is absolutely 0 or 0 Kelvin, how many dopant atom will get ionized?
0.
0, right? That means that all the electrons are at these locations only. Is that okay?
Yes, sir. Yes, sir.
Whenever electron will get this place, this to this, then this will become Nd plus, right? This particular atom, dopant atom.
Yes, sir.
So as all the electrons are in the dopant energy level only, so now if I tell you that f of Ed comma 0 is equal to what? Is equal to 1, right?
Yes, sir.
Probability of finding an electron at Ed or the dopant energy level at 0 Kelvin is 1. That means at 0 Kelvin your Fermi level has to be in this place, in this region. Why am I telling that? Because if my Fermi level is at this place, okay, if this is EF, then any energy level below EF should have full occupancy. So if ED has full occupancy, that means Fermi level has to be above that, this condition. This I have written wrong, I guess. For E less than EF, E less than EF, you have this is 0, this is 1, this is 0, right? So this condition will get applied. Do you see it? E equals to ED leads to me F of ED, comma 0, T equal to 0 is equal to 1. That means E of D has to be less than E of F, this condition. So one thing we got sure that EF has to be greater than ED, right? And again that if my electrons are at this place, then all the dopant atoms are ionized, or some of the dopant atoms are ionized. That is also not case. So EF cannot cross my EC also. Any question regarding this? So this will be the right answer. Anyone? Any question? There are two aspects of this question. First is that at 0 Kelvin temperature, no dopant atoms are ionized. Okay, that means all the electrons of the dopant atoms are possessed by that atom only. That means in energy band diagram, that is represented as that all the electrons are at this location only. Okay, and from Fermi-Dirac distribution, we know that at 0 Kelvin, if your Fermi level will be greater than that particular energy level where all the electrons are there. That means EF has to be greater than ED. If EF has to be greater than ED, that means it can lie anywhere above ED. Now what is the upper bound? Why EC? It has to be below EC. It has to be below EC because suppose if my Fermi level is at this location. Suppose you have this, right? This is your EC, this is EV, this is your ED, and it contains the electrons. Now from last discussion we know that my Fermi level can be above this. Okay, so now the question is, can it be at this place? It cannot be, right? Why? Because if this is EF at 0 temperature, that means EC is completely filled, or EC can be completely filled. When EC can be completely filled? When your ND plus will be equal to ND, but this is not true. We know that ND plus has to be equal to 0. That means EC or conduction band possess no electron, no free electron. Okay, if no free electron is possessed by EC, that means Fermi level cannot be above this. So this is not a valid solution. Okay, so your Fermi level has to lie in this region. EF has to lie between ED and EC. Okay. So let's move on to the next problem. Okay. It is given that an intrinsic silicon wafer is doped with 5 into 10 raised to 16 per this phosphorus atom and this much boron atom. Okay. Phosphorus atom. Okay. Just let me ask you this much. What is Na and what is Nd here? Anyone? What is the acceptor concentration and what is the donor concentration?
6 into 10 to the power 16
Is
Na, acceptor concentration.
okay.
5 into 6 to 10 to the power 16.
Okay. And it is also mentioned that that means boron is your acceptor, right? I wanted to check that whether you know this. Okay, assume that a 300, so T is given as 300 Kelvin. The intrinsic carrier concentration Ni is given as 10 raised to 10. And all the dopant atoms are ionized. That means your Nd plus and Na minus are same as Nd and Na. Okay. It is not always true. Remember that at whenever we go at lower temperature, the ionization also reduces. You see, and what is the extreme case? At 0 K, ionized atom becomes 0. We have discussed this in the last problem. But at room temperature, we are told to assume that this is the case. So this is 6 into 10 to the power 16 and 5 into 10 to the power 16. Okay. So from charge balance, what is the charge balance equation? Q of P plus Nd plus minus N minus Na minus equal to 0. Why do I do that? Because at equilibrium, my entire, what is equilibrium by the way? Thermal
The
equilibrium.
entire silicon wafer is electrically neutral.
Yeah, at thermal equilibrium, my entire silicon wafer has to be electrically neutral. Okay, so now if I take Q is a constant 1.602 into 10 raised to minus 19 coulomb, so I have this. Okay, for the time being, I am considering, I will prove it later that this quantity I am considering is very small and equal to 0. We will prove that why it is equal, why I am neglecting it in this discussion. So what is my P or whole concentration? Nothing but Na minus minus Nd plus. Okay, so that is nothing but 6 minus 5 into 10 raised to 16 centimeter cube or 10 raised to minus 16 centimeter cube, 10 raised to 16 centimeter cube. Okay, so if that is the case, at thermal equilibrium, we know my mass action law is also valid. What is mass action law? Mass action law says that N times P should be intrinsic concentration squared. Okay, so what is my N? Then Ni square by P. Ni square is given, Ni is given as 10 raised to 10, so Ni square will be 10 raised to 20 over 10 raised to 16. Okay, so 10 raised to 4 centimeter cube. Now you see the order of magnitude of difference between you see the order of magnitude difference between P, Nd, Na and N. The other three quantities are at the order of 10 to the power 16 and N is at the order of 10 to the power 4. It is 12 order less. So obviously we can neglect that. That's why we have assumed it to be 0. Okay. So even if you make such an approximation in your calculation, just cross check it, so that it is called self consistency, that the assumption whatever you are taking and you are deriving some solution, you just go back and check whether that assumption is correct or not. Okay, so this is the first step to check approximations in any kind of modeling exercises. So now you have your n. So what was asked to be find it out? What was asked to be found, that is, what is the location of the Fermi level with respect to the conduction band edge. Okay, so we have given that we should find out it with respect to the conduction band edge. So we will consider formula for n to calculate this. So n equal to nc exponential minus ec minus ef by kt. I think you know how to derive this formula. Okay, it is given in the lecture. There is a very simple integration you need to do with Boltzmann approximation, but you need to have the idea of density of states and Fermi distribution, okay, or Boltzmann distribution. What is this quantity NC? This is nothing but your effective density of state, okay, effective DOS. What is this? Your GCE, rather the conduction band, is of the form of E minus EC, okay. EC is the conduction band edge. So if I plot your G of E at this scale and energy at this scale, so and this is your EC, so it will be like a parabola, okay, fine. So if I ask you what is the density of state for electron at the conduction band edge at E equal to EC, what will be your answer at this point?
0.
Right, it will be 0, remember that. But you see, this NC we take as a effective conduction band, effective density of state at the conduction band edge only. Okay, why do we do that? When I know this is like a delta function, okay, means at E equal to EC only it is valid. This is just nothing but a mathematical manipulation of the effective density of state. Why do we do that? My question is that. When I know that at the conduction band edge my density of states is 0, right? The reason for doing this is, if you take Fermi energy or Fermi function at this place also, you will see this kind of behavior, okay? This is your Fermi profile. You go back to the lecture and you will see how this come about, okay?
Yes, sir. That is the multiplication. 0 into something that becomes 0.
Yeah, this is your Fermi energy. So you see, it will be something like this, right? This is 1, and around some this place you have this EF. This is your Fermi distribution. So what will be your N? N is nothing but your EC to infinity, your GC of E multiplied by F of E dE. Okay, this is how you calculate the concentration of electron. So if you multiply this function, this blue curve and this orange curve, you will get something like this. Okay, this will give you the concentration as a function of E. Then you integrate it, and this area under this violet curve will give you the concentration. Okay, this integration is nothing but that area only. So you see that the majority of the concentration of electron is lying at the conduction band edge. Okay, so that's why we assume is that for our mathematical convention that all the electrons lying at the conduction band edge only, though we know that exactly at the conduction band edge there is no electron, there cannot be an electron, because my density of state, there is no density of state. Okay, So you see the anomaly. So understand this very carefully, that at the conduction band edge, though there is no density of state present and actually there is no electron present, we consider for our mathematical convention that at the conduction band edge only the electrons will be there. Okay. This distance from the conduction band edge where the maxima of the electron occurs is your half of kT. Okay, this is I'm giving just for an information. It is a very simple proof, you can do it, but remember that if someone in some interview asks you that what is the electron concentration peak from the conduction band edge, because we know that at conduction band edge it is 0, it is around half of kT. This half comes about from this square root. Okay, so this NC is your effective density of state. Fine. So in question your effective density of state is given. Your NC is given as 2.82 to 10 raised to 19 per cc. Okay, and your N is 10 to the power 4, right? 2.82 into 10 raised to 19 exponential minus EC minus EF over KT. What is KT? At KT is nothing but 1.38 into 10 to the power minus 23 joule per Kelvin into 300 Kelvin. Okay, this result will give you in joules. Okay, now if you convert joule to electron volt by dividing it with 1 electron energy, you will get that it is 0.026 electron volt. Okay, so this is I am taking in electron volt. So if you solve this numerically, solve this numerically, solve this equation, after some numerical calculation you will find out that EC minus EF is coming out to be around your 0.92 electron volt. Okay, 0.92 electron volt. Yeah, so your EF will be around EC minus 0.92 electron volt. So the question was, with respect to the conduction band, what is the location? Okay, so this should be your answer. So tell me if you have any question in this problem. This is a very important question. If you want to do your MTech or PhD in any of the higher education institution, this question most of the time they ask. Okay, they ask that what is the density of state of electron at the conduction band edge. Remember, it is 0. And similarly, what exactly is the concentration, electron concentration at the conduction band edge? It is 0. But for our mathematical convention, we consider this term. Okay, so I think you have understood it. So let's move on to the next problem. It is mentioned that as temperature increases from 0 Kelvin to high temperature, the carrier concentration goes through 3 regions. In what order does that transition occur? So let me draw some graphs. Okay, and you tell me whether you have, just don't write this, carrier concentration. Okay, so this is one graph. This is region 1. region 2, region 3. This axis is T in Kelvin. This is carrier concentration in linear scale. This is around your 50 to 100 Kelvin, and this point is somewhat around 300 Kelvin, your room temperature. Okay, this is one plot. Another plot is this is carrier concentration. This is your log scale. This is your 1 over temperature, Kelvin inverse. Okay, so this is your 1 over Ti, and this is some temperature. So here you have. So can anyone tell me whether you have seen any of this region A, region B, region C? Any one of this plot have you seen? Which plot have you seen? This is the carrier concentration versus temperature plot. You can unmute and tell me whether you have seen any one of them, or if you, even if you do not have seen saw it, if you haven't seen it, that is also fine.
So seen in lecture, not exactly, but similar graph is there.
Which plot you have
When
seen? The right one or the
energy
left
and
one?
no
There is no
graphs
energy.
are and professor had make the graph between energy and Fermi level, and he changes the temperature, and so
No,
in
that
same graph
is
only.
no, that is this graph, right? Don't get confused. That is, see, again, there is some fundamental mistakes. Okay, the mistake is that you are trying to remember the shape of the graph, and from that you are trying to conclude that this is that graph only. Okay, please don't do that. The way to go about is that you understand the graph is between what. This was Fermi function and versus energy. This was Fermi energy, Fermi Dirac distribution over energy. Okay, this was that plot. Completely different context. This is carrier concentration. How many carriers are there per unit volume versus temperature plot. So it is miles apart, two things. Just because something looks similar to something doesn't mean that they are both are the same thing, right? The atoms are also spherical and a cricket ball also spherical. Those are not the same thing. So the context is that carrier concentration versus temperature plot. Have you seen this kind of plots anywhere, anyone?
So the first diagram was in the lecture, sir.
First diagram you have seen the linear versus temperature scale. Okay.
Yes, sir.
Okay. So what happens basically? First, tell me that how many ways. Let's talk about n-type material. Let's say doesn't matter. N-type material is having more number of electrons, right?
Yes, sir.
More number of electrons in. Here you can keep yourself unmuted. Let's have a discussion. It will be better.
More number of electrons in conduction band.
Electrons in conduction band, exactly. That means the free electrons, right?
Yes.
So how many ways there can be free electrons in an n-type material?
Through the donor atoms and from the silicon from the valence band of the silicon layers.
from the valence band of the silicon atom, that is called intrinsic carrier concentration.
sir.
That will create equal number of holes also, right?
Yes, sir. Yes, sir.
Means whatever Srihari is told for others to understand, that if something goes from here to here, that leaves a hole here, right? And creates an electron here. And also remember that in n-type material we have a donor energy level here, ED, which possesses these electrons, extra electrons. This transports here and creates some electron. And what happens to this? Do we have hole here, or what do we have here? We have Nd plus, right?
The atom will be neutral.
Now, though atoms will be neutral, but if that atom donates an electron,
Ions. You will have
it will
immobile ions.
immobile ions, right? Exactly, that will be an immobile ions. So one is way that this phenomena we are calling at intrinsic carrier. It creates one hole and one electron, but this way, this due to you say dopant ionization. This creates one electron but one immobile ion. Okay, so these two way we can have free electrons in the conduction band for a silicon, right? Now this carrier concentration is free electron carrier concentration. Okay, now think, I just want you to think with me. Suppose you are at a 0 Kelvin temperature. Okay, what will happen at 0 Kelvin temperature? How many electrons should be there? Free electron. Now let's start with 0 Kelvin, T equal to 0 K. Free electron concentration should be 0, right? Because both of my process do not contribute. Why? Because at 0 Kelvin temperature, no electron will go from valence band to conduction band, and no dopant atoms will also get ionized. So it will be 0. Now think about this. Your Ni is equal to some root over Nc Nv exponential minus Eg by 2 kT. Okay. So for silicon, okay, let me ask you in this way. Let us not go mathematically, let us go qualitatively. Suppose, tell me one thing, that what do you think, that which energy is easier for the electron to overcome, this energy or this energy?
The energy between ED and EC is easier than EV and EC.
Right. So if I start increasing my temperature or KT, after some increase of temperature, this starts to get ionized first. Is that okay?
Yes, sir.
And if we increase the temperature much more, then only, if we have sufficient higher energy, then only we will have this surmounting of electron from EV to EC. So as we go from T starts to go from 0 plus Kelvin and increase, first thing is that electrons move from ED to EC. Okay, then after some time both will start to take place. ED to EC transition will also be taking place, and EV to EC transition will also be taking place. Fine. Now tell me one thing, do we have infinite reservoirs for electrons for this Nd? We do not have, right? We have some limited dopant atoms. Okay. Now think it in this way. After your 10 to the power 15 per centimeter cube, let's say if this is Nd and all are getting ionized, So follow me on this curve, okay? So as your temperature is increasing, so your this curve is due to the, let us call first, this is called second. This is the due to the second effect, okay, or dopant ionization. As we increase the temperature from 0 Kelvin, first thing will happen is that the dopant ion starts to get ionized. Why? Because this energy is lesser. The difference from conduction band is lesser, okay? So after some time, what happens is that all of my dopant atoms gets ionized. Then that those dopant atoms cannot contribute to further increment in electrons. Okay. After this condition happens, all the dopant atoms get ionized. So after certain temperature, all electron for due to the dopant atoms will be at conduction band. So this will get saturated. Okay. This trend will be like this. Now let's move back to the first case. What will happen to this intrinsic case? First thing we notice that at high temperature it will start to occur. Okay, so at high temperature it will start to occur, and then it is an exponential function of temperature. Okay, so it will start to get increasing, and these intrinsic atoms will start to dominate, because after sufficiently high energy, this silicon atom starts to break down, start to form electron hole pair. An electron will be generating here and holes will be generated here. Okay. So what happens if you take the net carrier concentration for both the cases, due to the dopant atoms and due to the silicon atoms or the intrinsic atoms, intrinsic silicon atoms? What happens? Both the electrons will try to populate the conduction band. So the conduction band electron concentration should be addition of these two phenomena. So now I just simply need to add these two graphs, right? 1 and 2. If I add 1 and 2 graph, what do I see? I see that this kind of trend. Okay. So if I just, if I draw it with temperature and carrier concentration, it will increase, then after some time it will start look like this. Okay, and you now know how this is coming about. Okay, this part is coming about due to the dopant part, and after that the intrinsic part start to dominate. Okay, this plot we divided into 3 regions. This region is called intrinsic region. Okay, this region is called extrinsic region. By the way, can you tell me what is this level? Just by mere inspection?
Out.
No, this level, the y-axis level, this level.
N equal to ND.
This is ND, right? N equal to ND. You are absolutely right. Because all my dopant atom are ionized. And what is this? At this place, N equal to? Shriyari, what will be this?
0.
No, it will be ND plus, right? 0 is only at this point. Understood, right?
Yes, sir.
Because here only some portion of the dopant atoms are getting ionized. This is also ND plus, but this is all are ionized. Okay. And what is this? What is this place? This is N equals to Ni. Right? Intrinsic carrier concentration. Remember that 10 to the power 10 per centimeter cube is only at T equal to 300K. Now if you make 3 equal to 1200K or around that, this 10 to the power order will be very large. Okay, so don't confuse that my 10 to the power 10 is a sacrosanct number. That number is only valid for t equal to 300K. Okay. So this region is called, by the way, freeze out region. Okay. So as we increase T from 0 Kelvin, this is 0 Kelvin, what happens? The carrier concentration goes first from freeze out, then go to extrinsic, then go to intrinsic region. Okay. Same plot, if you do it in log scale and 1 over T, it will be like this. So this region will be your intrinsic, this will be extrinsic, this will be freeze out. Okay. So these two kind of plot you will see interchangeably in all the books. Okay. Whatever book you open, either you see this plot, left plot, or the right plot. So just you don't get a surprise when you see the right hand side plot. That's why I have introduced that also. Okay. Now tell me one question. In which region do we generally prefer to operate? We prefer to operate in this flat region or the extrinsic region. Right? Why?
We do not want to vary the. We want to vary the signal with respect to input
No
signal.
no signal.
No, matlab electron, anything we want to vary.
No, not anything. Be specific. Carrier
Sir, we are
concentration.
operating at room temperature, sir.
We
Free
do not
electron.
want to vary electron.
Yeah, no. Tell it. What is that? You need to get accustomed with the terminologies, right? Free electron or free carrier concentration. Free carrier concentration, you do not want to vary with temperature, right?
Yes, sir.
Why?
Sir, we will be preferably operating at room temperature itself.
That is very fine. That is one reason that we will be preferring T equal to 300K. But that is not the question. Question is that at extrinsic region, we do not want to vary the conduction of carrier concentration with T, right? Why? The reason because what is a semiconductor, by the way? What is so special about semiconductor?
Control
of
electron, flow of electron.
No, control of the conductivity.
Yes, sir.
Right? Control of the conductivity. So sigma is my conductivity. This is nothing but N into Q into mu E for electron. Okay? And sigma of hole is nothing but P into Q into mu of hole. Okay? Now if we focus on these terms, these are the free carrier concentration. These are the same thing which I am plotting in x-axis or y-axis. Okay. So conductivity of the semiconductor, we want to have a control over. That control we want to have by what we want to control that?
By the number of free charge carriers.
No. Exactly the number of free charge carriers. How do you want to control that?
By controlling the temperature.
No, we don't want that. Right? By controlling, if I want, yeah.
By controlling the electric field.
No. Again, how these are the only two mechanisms through which you can get free carriers. I don't want my temperature to control the carrier concentration. That means I don't want because it is a strong function of temperature, intrinsic. Okay, I don't want intrinsic carrier concentration to get controlled. So I want I want doping to control it. Okay. Suppose I want to make a semiconductor of conductivity X. So I will dope that semiconductor accordingly. Now suppose I want to get a semiconductor of 10x doping. So 10x conductivity, 10x electron concentration. So I will dope the conductor 10 times, right? So I want my control handle to be this, control to be doping only. So doping will control N and P. This will control the sigma N and sigma P, or the conductivity. So the conductivity of the semiconductor I want to control by doping only. Understood? I don't want it to vary over temperature, because suppose one same mobile phone what I am, or cell phone what I am using in India, if I am taking it to Greenland or Iceland or some Scandinavian country, the performance will change drastically, because the temperature is changing in a wide range. I don't want that, right? I want my handset to be working at that place also. Understood? Anyone who didn't get this point? Parthasarathy or Srihari, anyone?
Understood, sir.
You understood, right? Why do you want to control the free carrier concentration via doping only and not via temperature?
Yes, sir.
Okay, this is very important. Okay, so now by using the formulas, you can see why silicon was preferred over germanium. Okay, silicon was preferred over germanium due to one of the main reason is that for germanium this range, extrinsic range, is very small. Okay, that we do not want. We want this extrinsic range to be, constant range to be wide, because that means if I am doping with Nd or Na, I will have that much particular amount of carrier concentration. That will determine my conductivity of the semiconductor. Okay, so this was a very important concept. Okay, so let's move on to problem number 5. Okay, an intrinsic germanium wafer is doped with a shallow acceptor density of this, where N plus is intrinsic carrier concentration at room temperature. Okay. Okay, so first thing I write the charge balance equation, P plus Nd plus minus N minus Na minus equal to 0. So P plus what is, only acceptor atoms are present, so this will be 0. What is my N? N will be there, and what is my this? This Na minus is nothing but 3Ni by 2. Okay, because Na minus is equal to Na equal to 3Ni by 2. It is given in the question. Okay, let me just zoom it so that you can read the question. An intrinsic germanium, see, acceptor density is this, that means Na is this, and temperature T, all acceptors are ionized, that means Na minus is equal to Na. Okay, so now what we do, we know the law of mass action, so we wanted to calculate hole density at temperature. Okay, so P minus Ni square by P minus 3Ni by 2 is equal to 0. Fine. So I have 2P square minus 2Ni square minus 3Ni into P equal to 0. So your P will be, this is nothing but a quadratic equation. We can solve it, and one root will come negative. So if we calculate, we will see that P will be equal to 2Ni. Okay. So should I do it from this to this step, or you can do it yourself? How much time do you have? Okay, we do not have much time. Okay. Okay, just let me do the next problem also. Yeah, I think you can manage to solve this quadratic equation. Okay, it is nothing but this x equal to minus b plus minus root over b square minus 4ac by 2a. Okay, this is the same thing, x square plus bx plus c equal to 0. If this equation solution is this, I think you can manage. Okay, so your 2 and I will be the right option. So going to problem number 6. Under which condition the position of Fermi level in the intrinsic bulk semiconductor lies exactly at the middle of the band gap at a non-zero temperature? Okay. So what is the condition? By the way, I think you all know this, but I want to show you the proof very briefly. You see your Ni has an expression of this, right? And also you have an expression of this minus Ec minus Ei by Kt. Okay. If you just equate them, so you get what? You get that root over Nv by Nc equal to exponential minus Ec minus Ei by Kt, and this will be plus Eg by 2Kt. Okay, so it will be ln Nv by Nc. This root will come as half, and here you will get Ec minus Ei by Kt plus Eg by 2Kt. Okay. By the way, what is EI? EI is nothing but your intrinsic Fermi level. Okay. So you have what? Half ln Nv by Nc is equal to minus Ec by Kt plus Ei by Kt plus Eg by 2Kt. Okay. So if I take Kt over 2 here, Nv by Nc is equal to Ec minus Eg by 2 plus Ei. So if I calculate Ei, it would come out to be Ec minus Eg by 2 plus Kt by 2 ln Nv by Nc. Okay. So now I want this to be equal to this. Okay. So that means my this term should go to 0. How can this go to 0? This term should go to 0. So ln of
Either the
x,
temperature is 0 or the effective mass of electrons
right,
is 0.
ln1 is 0.
right, either my temperature has to be 0 or ln of this x equal to 0 when x equal to 1, right? So the plot of x of ln x is something like this. Okay, at 1 it becomes 0. Okay, and at 0 it becomes what? What is ln 0? Anyone?
Not defined, sir.
It is minus infinity. Okay, yeah, not defined is also correct, but it is minus infinity. Why it is minus infinity? Because e to the power minus infinity is 0. Okay, we have discussed this thing a few minutes back. So if this is such that, so your Nc has to be equal to Nv for Ei to lie at the center of the band gap, And what is NC? NC is nothing but 2 pi m star E kt over h square 3 by 2. Similarly, 2 pi mp star kt over h square over 3 by 2. I was using mh, right? Okay. So from this you see this has to be equal. Okay. So the effective mass of the electron and the hole has to be equal for this to be satisfied. Okay. So D is your right option. This is how the proof is. And by the way, can you tell me what is more in them? Effective mass of electron or hole, what is more in silicon?
Effective
Sir, I have
mass
a
of
small
hole.
doubt.
Effective mass of hole is more, right?
Yes, sir.
How do you tell that? Means we know that, but why do we tell that?
Moment in valence band is less crowded and conduction
Yeah,
band is less crowded and valence band is more crowded. So
no,
moment
right?
is
Well, yeah, that is
critical.
one way. That is one way, but we can tell it from EK diagram. Okay, the more theoretical one and the more exact one. From how can you tell from EK diagram that hole will be like that? Your m star is nothing but h bar square
Double
by,
differentiation.
right, del k square. So m is more means this is lesser. Okay, so that means for electron, just let me do it this way. For hole it will be a flatter one. Okay, though the k I am not considering because the silicon is not direct band gap, so it will not be at the same k point, it will be some different k point. Okay, but you see that the curvature of the conduction band is more in case of electrons, right? So that means this is more, that means m star is less, and for holes it is just the opposite. Do you get it? Why the thing is
Sir,
like that?
sir, can you repeat, sir? The valence band curvature is less so that the effective mass is high.
Valence band curvature of the hole is lesser, so your m star h is higher. Okay,
Okay, sir.
and what if these two, if this condition has to be met, then what should be happen? The curvature of both the things has to be same, right? Did you get it?
Yes, sir. Sir, in any curve, is double differentiation give curvature?
Yes, that is how it is defined. But there
Okay.
are conditions that derivative has to be existing.
Yes, sir.
If the derivative does not exist, it will not give any curvature. The thing we have discussed in last class or last class, I cannot remember, for graphene case, right? Where the energy band diagram was like this, then there no derivative was existing. So
Yes, sir.
the effective mass itself was not defined, right?
Yes, sir.
So okay, so that was it for today. I think we are well past time.
Sir,
Yeah,
sir, I have a small doubt, sir.
yes, please.
So, generally, for an intrinsic semiconductor, we should not say that the Fermi level lies exactly in the middle. Is it right or wrong, sir?
Exactly right.
We should, it is, then what is the answer, sir? It is not in the middle.
It is not in the middle because the effective mass of the holes and the electrons are not same,
Okay, sir.
right? You can
Yes,
even you can calculate, right? I do not know these problems. This sessions is designed such that I cannot explain much more theory. Okay, but you can actually calculate from how difference it is from the EI, the intrinsic semiconductor thing is exactly from Eg by 2. Okay, this quantity you can exactly calculate. This thing you can exactly calculate. You see from this formula only, right? That
yes,
this
sir.
is your thing, but this formula, what do you need for this to get calculated? You need just these values, right? Sorry, you need just these effective mass values. Other thing, everything you know, KT you know, temperature you will be given, H bar H is you will be given. So if you know
Yes,
the
sir.
M star of any material, you can easily tell that for that material whether they are lying at the middle or they are near to the near between EC and EI, EC and the middle, or EV and the middle. Okay, that can be calculated from this quantity.
Okay, sir.
Okay,
Hence, for silicon, EA is not exactly in the middle.
for silicon it is not in the middle because of this thing. Okay, the curvatures are not same. And
Generally,
please,
for an intrinsic semiconductor, there is an offset value from the middle, either above or below.
it depends actually. See, it will never be in the middle. Let me tell you that.
Okay, sir.
Why? Because two curves, these are very random things. Okay, this band structure, whatever you are getting is very, I mean, the abstract quantities and very random things. There are a lot of computation you need to do to find this out. So you will never get exact same effective mass anywhere. Okay,
Okay, sir. Okay, sir.
and also please note that this band diagram is not absolutely correct. K in K there will be variation for silicon. Okay, means your this will be here and this will be somewhat here. This is called indirect band gap semiconductor. Silicon is indirect band gap. Okay, so this is not for silicon. Okay, so on that note, can we conclude today? Or if you have any question, I would like to answer. Okay,
Thank you,
yeah,
sir.
okay, okay. Thank you. So let's meet next next Sunday. Okay, thank you.